In this video, we'll take a closer look at gas law calculations. The first gas law we'll talk about is Boyle's law. Boyle's law tells us that as the pressure increases on a gas, the volume of that gas will decrease. Pressure and volume are inversely related according to Boyle's law. Let's work a sample problem using Boyle's law. We have 20.5 liters of nitrogen gas held at room temperature, which is 25 degrees Celsius, and 742 torrs of pressure. That sample's pressure is increased to 9.8 atmospheres. Assume that temperature is held constant. What would be the new volume at this pressure of 9.8 atmospheres? Remember, Boyle's law is P1V1, that is the pressure times volume at one set of conditions, equals P2 times V2, that is the pressure times volume at a second set of conditions. Let's plug in the values that were given for pressure and volume and solve for the unknown. What we're trying to solve for is a new volume, in other words, V2. Since we want to solve for V2, we would like to isolate it on one side of the equation, and we're going to do that by dividing both sides of the equation by P2. Doing so, we get that P1 times V1 divided by P2 equals V2. Now all we need to do is plug in the values that were given to us in the problem for P1V1 and P2. You may have noticed that the initial pressure was given in units of torr, and that the final pressure, P2, was given in units of atmosphere. Both the torr and the atmosphere are non-SI units of pressure. 1 atmosphere is equal to 760 torr. When using any of these gas law equations, units must match so that they cancel out. So let's go ahead and convert 742 torr to atmosphere so that our pressure units match. The conversion factor we need is that there are 760 torr in 1 atmosphere, so we can convert from 742 torr to atmospheres by placing what we start with, the 742 torr, in the upper left-hand corner of a conversion chart, then bringing down the units of torr. Place 760 torr in the denominator and 1 atmosphere in the numerator. Then, when we multiply 742 times 1, we get 742. And when we divide that by 760, our answer is 0.976. And since the units of torr canceled, we are left with the units of atmosphere. And that tells us that 742 torr is equal to 0.976 atmosphere. Plugging all our values into the rearranged Boyle's law, we get that 0.976 atmosphere times 20.5 liters divided by 9.8 atmosphere equals 2.0 liters. You give it a try now. Here's a real-life problem that operates on the principles of Boyle's law. On October 14, 2012, an Australian skydiver and daredevil, Felix Baumgartner, jumped to Earth from a helium balloon in the stratosphere. He set multiple records on that date, including being the first person to break the sound barrier without vehicular power. On the ground before his takeoff, Felix's team filled his balloon with 5.10 times 10 to the 6th liters of helium as he prepared to take off. The atmospheric pressure at the launch was 1 atmospheres. When he jumped from approximately 39 kilometers from the Earth's surface, the volume of his balloon was 8.50 times 10 to the 8th liters. What was the atmospheric pressure on his balloon the instant Felix began his 4-minute and 19-second freefall towards Earth? When you're ready, press pause, work the problem, and then press play to see if you got it right. As you saw in the first example, we rearranged Boyle's law to solve for the desired variable. In the last problem, it was the new volume. In this problem, we are solving for the new pressure, or according to the equation, P2. P1, or the original pressure, was 1 atmosphere. The initial volume of the balloon was 5.10 times 10 to the 6th liters. The new volume of the balloon was 8.50 times 10 to the 8th liters, right before Felix jumped. We needed to solve for the final pressure, so we rearranged Boyle's law to isolate P2 by dividing both sides of the equation by V2. Once we plugged in the values that we had for P1, V1, and V2 and solved, we found that the external atmospheric pressure on Felix's balloon was only 0.006 atmosphere. This makes sense because at that altitude there aren't many gaseous molecules that can apply an external pressure on his balloon. The second gas law we're going to look at is Charles' law. Charles' law examines the relationship between volume and the absolute temperature of a gas. In this case, volume and absolute temperature are directly proportional to one another. That means as volume goes up, temperature must also go up. Let's work an example using Charles' law. A gas that occupies 247 milliliters at 22 degrees Celsius is heated to 98 degrees Celsius. Since pressure is not mentioned in the problem, we will assume pressure is held constant. What would be the new volume at 98 degrees Celsius? Looking at our rearranged equation, that would be V2. Let's write down Charles' law to remind us what we're working with. V1 over T1 equals V2 over T2. Since we're trying to solve for the new volume, or V2, we'd like to isolate V2 on one side of the equation. We're going to do that by multiplying both sides of the equation by T2, and that will give us the rearranged Charles' law shown here. Now we just plug in the values that were given to us in the problem. Remember that temperature must be in Kelvin. The initial volume was 247 milliliters, and the initial temperature was 22 degrees Celsius. We need to convert that to Kelvin, which you do by adding 273 to the Celsius temperature. 22 degrees Celsius is the same as 295 Kelvin. The final temperature was 98 degrees Celsius. Again, we need to convert that to Kelvin, so we add 273 to the Celsius temperature to convert it. 98 degrees Celsius is the same as 371 Kelvin. Now we have the equation 247 milliliters times 371 divided by 295. And now we carry out this calculation and we will get the new volume. V1 is 247 milliliters. T2 is 371 Kelvin. Our final volume, therefore, is 311 milliliters. Just as we expected from Charles' law, the volume of the gas increased due to the increase in temperature. Here's a problem for you to try. A helium-filled balloon has a volume of 2.9 liters at 33 degrees Celsius. The volume of the balloon decreases to 2.48 liters when it's placed outside on a cold day. What does the temperature outside have to be in order to cause the volume of the balloon to decrease to 2.48 liters? Make sure you report that temperature in Kelvin. Pause the video while you work this out, and when you're ready, press play and check your work. It's usually simpler to work out these gas law calculations by listing the given information in the problem. One of the most common mistakes students make is not matching the correct volume and temperatures together, so be careful with that. Your original volume was 2.9 liters. The new volume was 2.48 liters, so volume has decreased. What do we expect to happen to the temperature according to Charles' law? Remember, they are directly related, so we would expect the temperature to also decrease. So we're expecting T2 to be less than 306 Kelvin. When you rearrange Charles' law to solve for the new temperature and plug in the values, you get that T2 equals 261.7 Kelvin. In fact, temperature did go down from 306 Kelvin. The final gas law we're going to work with in this closer look is called the Gay-Lussac law. We've examined all combinations of the four variables that describe the properties of a gas except for pressure and temperature together. And that's exactly what Gay-Lussac law does. It turns out that pressure and absolute temperature are also directly related. We've done enough of these gas law problems so that you can probably work a sample problem by yourself. Let's give it a try. According to the National Football League, NFL footballs must have an internal pressure of 0.85 to 0.92 atmospheres to be considered legal. Footballs at pressures under 0.85 atmospheres are considered illegal because they are easier for quarterbacks to grip and throw. If the temperature inside the field house in Foxborough, Massachusetts, where footballs are inflated during pregame, is 294 Kelvin before kickoff, and the initial pressure of the football is 0.88 atmospheres, will the footballs be at a legal pressure at halftime of the game? Assume the temperature on the field is 275 Kelvin. What will the pressure of the footballs be at halftime? Go ahead and press pause, and when you think you have the answer, press play and check your work. Did you find that the final pressure was 0.82 atmospheres? If so, good work. If not, let's take a look at how we arrived at this answer. The first thing we did was rearrange Gay-Lussac's law so that P2 was isolated by itself. Next, we plugged in the values given to us in the problem for P1, T2, and T1. And then we solved for the final pressure, P2, and found the pressure inside the football was 0.82 atmospheres at halftime. So we have evidence that the football would have a lower pressure due to a lower temperature. And that's a closer look at gas laws calculations. For more chemistry matters, be sure to check out our website, where the entire series is available to you.